Hello. So this lecture is going to be on Thomson 6.2, and I'm pretty excited about this section. This is where we're actually going to calculate a cross-section for a real process. Okay. In what chapter was that? In chapter 3, right? We did some toy model where instead of dealing with particles with spin, we assume that if the particle has no spin, these MFI stuff in the cross-section calculation or the decay calculations that we did in chapter 3, right? These will just turn into G's of whatever type of interaction we're dealing with, right? Okay, but since we know that, right, the electron has spin, photon has spin 1, but then we found out from the last section is that we actually only have two polarization of it, either vertical or horizontal, and therefore you actually only sum over two of them. We already took care of that, but okay, now we're going to have to see what these spins are going to look like when we have to add up all these different possible ways that this particular annihilation process where we're doing electron-positron annihilation that turns into a photon, and then let's say it decays into a mu plus mu minus. Doesn't have to decay into that, but let's just deal with this process for now. Okay. So to calculate the cross-section, we need to get all the pieces of this equation from chapter 3, where this equation tells you that what's known as the differential cross-section, right? This sigma here is the cross-section. The omega here, omega is the solid angle, okay? And when we used to integrate that, it would just get 4 pi. But now we're not going to get 4 pi anymore because, right, if we account for the spin of these interaction, this MFI is going to have some angular dependence that we're going to have to account for. So when we do that integral, we don't get just 4 pi anymore. Just to remind you what these other factors are, right? 1 over 64 pi square. That's just from a bunch of 2e's, right? There's a bunch of 2's that got factored in. The pi is this geometric. This S here, right, is the center of mass energy squared. Right, remember S is actually equals to P1 plus P2 squared, right? So it has units of actually GeV squared, okay? I remember that some people made that mistake in the first exam where, you forgot to square P1 plus P2 in order to calculate S, okay? PF and PI are the incoming and outgoing, outgoing and the incoming momentum of one of the particles, their magnitude in this center of mass frame. And this MFI thing is what we actually spend 2 chapters calculating, right? Starting from the Dirac equation to the last chapter, we actually found out how to use the Feynman rules in order to do these calculations, okay? We actually did it with the pure Dirac equation method for, I think, what was it? It was an electron scattering off a tau. I think that was the one we did manually, okay? But we actually found that, from this example, we actually found that, there's some Feynman rules. There's some rules that we can follow in order to write this matrix element pretty quickly, okay? For E plus E minus, annihilation into mu plus mu minus, okay? This particular process will have this following the Feynman rules. You'll find that it has this particular matrix elements. In fact, do I go through it? I think I went through it pretty detailedly last time already. But I'll just highlight what the different parts are, right? So you have E square, right? That just come from each of the vertices. E square is in fact alpha, right? So, proportional to alpha, it's actually E squared over 4 pi. Okay, this Q here is the momentum exchange, which was going to be, in this case, right? Let's not have this around anymore, right? Let's go down here, right? We have an electron coming in with some momentum P1, right? And a positron coming in with some momentum P2. So remember, the momentum is actually going forward, but then the particleness is actually going backward, right? So don't let this particleness arrow trick you. Okay, so the momentum of this Q is actually P1 plus P2, okay? And then, of course, you're going to square that, and that's going to just turn into S, but we'll see that in a little bit. This G mu nu came from summing over all the possible polarization states of the photons, okay? This part is the electron current, where the electron current is this J mu. So this mu is the Lorentz index, which is 0, 1, 2, 3, right? It's not the muon. And then down here you label it muon. So hopefully there's a little bit of muon confusion, but hopefully is we just have to be very careful about which Greek letter means what. Okay, so this current, right, is just this gamma mu sandwiched between these two spinors. Okay, this is actually the adjoint of a spinor, which has an additional gamma knot in it, but we don't have to worry about that now. Okay, this part is the muon current. Okay, so this is the electron current, this part, right? This whole flow of electron, right? The second half here, right? This part here is the muon current. Actually, it goes the other way, sorry. Okay. Okay. Similarly, right, it has, this gamma, instead of gamma mu, is called gamma nu because you have to have a different index between the two currents. Okay, it's just a different Greek letter. There's nothing significant about the Greek letter nu. Okay, and this is the muon current, so that's why you have J mu, right, with the index nu. Okay, and it's also sandwiched. This gamma mu is also sandwiched between these two spinors. Okay. Okay, and these momentum corresponds to the outgoing momenta, right, for the muons. So this shortened this matrix element thing, right, to minus E squared over Q squared, G mu nu, and then you're going to have to deal with these currents, okay? And then once again, I just substitute in that Q squared is actually equal to S in this case because we have the two incoming momentum being joined together to add together into the Q, right? Because P1 plus P2 equals to Q just from conservation of momentum. Okay, and therefore, right, this Q squared is actually equal to S. Okay, so the matrix element just actually gives you another factor of S on the denominator. Okay. And remember from the homework, we're going to deal with this problem in the center and mass frame. In the center and mass frame, square root of S is actually 2 times the energy of the two particle beams coming together. Okay, so if you have a E minus coming in here, this will have some energy, the beam, right? And if you have a E plus coming in here, this will also have equivalent energy because you are in the center mass frame. The two energy has to be the same, otherwise you're not in the center mass frame anymore. Okay, they collide, the amount of energy in these two beams is just twice the energy of each of the beams. Okay, each of the electrons. Okay, right. So that's nice. Okay, so these currents, okay, are going to be more interesting because these currents actually have these spin stuff or these helicity stuff in it. Okay, so the book is flipping back and forth between spin and helicity. In these high energy regimes, they're actually the same. Okay, there are some caveats that there are slightly different things, right? Remember that spin does not commute with the Dirac Hamiltonian, and therefore they don't share eigenstates, but helicity share eigenstates with the Dirac Hamiltonian. So technically, we are always talking about helicity. Okay, but it's just a lot of times when we're dealing with high energy particles, they turn out to be the same thing. Okay, so let's deal with the helicity. Let's just cross that off of all these different particles that's coming in and out. Oops, that's actually the polarization of the photon, so that's okay. Okay, So we have to deal with the helicity state. So I actually typed that correctly, even though it says spin sum over here. Okay, so this incoming electron, right, can either be right-handed helicity or left-handed helicity. Okay, remember, right-handed helicity is where if you follow the direction of the momentum, right, your hand's gonna curve in the same direction if you're using your right hand, but where your left hand, it'll curve in the opposite direction. Okay, right. Similarly, this anti-electron is also can be possibly right-handed or left-handed. So already, like let's just deal with this left-hand side here, right? Already, let's go the blue. You can have right, right. You can have right, left. You can have left, right. You can have left, left. Those are all the different possible ways that these photons, these electrons, can come into this vortex. So there's actually 4 different possibilities. Okay, we're going to see that, right? We're going to average over this. We're actually going to multiply everything that we calculate by 1/4 because of this. Similarly, right, the muon that's coming out can also be right-handed, left-handed, right-handed, left-handed. So there's also 4 possibilities for this to happen. Okay, the photon, we already accounted for this. There are actually also 4 different polarization state, but we accounted for this by summing over all of them, and that actually turns out to be this negative G mu nu factor that we have in the matrix elements already. Okay. All right. So labeling these things slightly differently. Okay. So let's say, right, I'm going to highlight this in purple. Okay. Let's say we have, ooh, that's a really weird color, but okay, right. Let's say we know that the 2 incoming electrons are actually both right-handed. Okay. So the way you would write that is that, well, some matrix element, right? And this matrix element is both incoming right-handed. Okay. But, right, this photon can decay into these 4 different possible outgoing helicity states. So therefore, this can actually decay into 2 right muons. So these are the electrons, right? Or it can decay into a right and a left. It can decay into a left and right, and it can decay into 2 left-handed muons. Okay, right. So already, right, just for 1/4 of these possibilities, there's already 4 terms. Okay, guess what's going to happen? Okay, right. In order to account for all the possible incoming electrons, right, we have to average over all the incoming electrons. So these first label here, right, these are the incoming possible electrons. Ugh. Okay, and each of these flies off into 4 different terms. Okay, so you have this times with 4 terms, you have this with 4 terms, you have this with 4 terms, you have this with 4 terms. So there are actually 16 terms here. Whew. Right? I'm not even going to try to write those out. It's just going to take forever, right? So in general, when there are 2 possible helicity states, right, the average, so I just want to make sure to highlight that this little bracket stuff around here is the indication of averaging, not, Barquette notations, okay? Because by averaging over all the 4 possible incoming helicity states for the electrons, right, we take each of them, right, and then if we divide by 4, then we're just averaging over those 4 different possible ones, okay? So in general, right, when you have 2 possible helicity states, you actually want to take the average matrix element squared, right? And so you're summing over all the different spins and then dividing by 4. Okay. All right. So now we're going to make one more concession to make the calculation a little bit easier to deal with. We're going to go to the high energy limit, where basically whatever the energy of the incoming and outgoing particles are is going to be much bigger than the mass of each of the particles. Okay. right? And let's see what this does to simplify our calculations, okay? So here on the right, we still have our old Feynman diagram. Great, we're already familiar with it. Drew this like a million times, right? On the left-hand side, we're going to have a physical diagram where I think this is going to be the z-axis is going to go along the horizontal, and I think the up and down on the screen is going to be the x-axis. Okay, so you have a incoming electron coming in, and incoming positron coming in with momentum p1 and p2. Okay, they annihilate each other at this interaction point, and then decay into, and that photon decays into p3 and p4 as muons instead. Okay, and this angle here is going to be defined as basically the polar coordinate angle theta, where it's relative to the z-axis. Okay, remember the positive z-axis is along this direction, right? Okay. All right. So now let's write these four momentas. Okay. So P1 is pretty easy, right? So P1 is going to be, let's just write this out first. Okay. P in general is going to be gamma m. Okay. Okay. Of the electron. Okay. 0, 0. Okay. Gamma m v of the electron. Okay. So those are the general momentums, okay, if you were traveling in the z direction, okay. In this high energy limit, okay, basically, right, gamma me is going to become the energy of the photon, okay, because we don't have to worry about the mass at all, okay. And since gamma me is energy, v is basically going to be about 1, okay. It doesn't actually ever reaches the speed of light, but in high energy limit, right, you're basically pushing this particle until it approaches the speed of light. So basically, the forward momentum for the incoming electron, right, is just going to be E in the time-light component, which is the energy component, and then the Z component is going to give you E also. The positron's momentum is going to be very similar, but since it's going in the opposite direction along Z, the sign is flipped to negative E for the Z component. Okay. P3 and P4 requires a little bit of geometry. The energies are still the same because they come in so much energy. The mass of the muon does not take away that much energy from the process. Okay. But, right, doing a little bit of geometry, you're going to find that, well, momentum 3, right, is going to be sine, the x component is going to be sine of the energy times sine of theta, and then the z component is going to be the energy times cosine of theta, and then P4, so this is the mu minus, this is the mu plus, okay, P4, right, it's going to be very similar to it, but then it's going to be in the negative direction, just because they're both going to go in the opposite direction, right? So one thing to notice is that, right, the electron, positron are always in the opposite direction. The muon and the mu plus and mu minus are also in the opposite direction. Okay. All right. So in this high energy limit, right, we found from chapter 4, okay, that the right-handed helicity and the left-handed helicity for the particles, right-handed helicity for the antiparticle, left-handed helicity for the antiparticles, okay, can be described by just these, the simpler version of the equation, where the book shorthanded this, right, and where C, right, is actually cosine of theta over 2, and then S is sine of theta over 2. Okay, so these are sine and cosine function, and then you have some exponential e to the 5 with that. Okay, so plugging these angles in for the electron, so electron is a particle, so we plug them into the particle left and the right-handed spinners. Okay, so cosine of 0 is going to give you 1. So let me just make sure we're following the logic here. Cosine of 0 over 2 is still 0, and therefore it's 1. Okay. Similarly, sine of 0, right, is 0, okay? And then cosine of 0 is also 1 again, and then sine of 0 is 0. So that's how we get this spinner, okay? Right, for the left-handed spinners, okay, we have sine here. Sine of 0 is 0. Cosine of 0 is 1. E to the 0 is also 1, so therefore you actually get just 1 there. Okay, sine of 0 is 0. Cosine of 0 times ei phi of 0 is also 1, but then you have a negative sign in front, therefore you get the negative sign there. Okay, whew. Okay, so that simplifies quite a bit. Okay, at least we can multiply by 1 a lot. Okay, so for the positron, right, the positron is coming in at an opposite angle to the electron, right? If you have something going in opposite angle, what happens is that you basically flip that angle 180 degrees, right, both in the theta and phi directions. So therefore, right, whatever the positron's coming in, position positron coming in, right, the angle of it, if we declare that the electrons coming in at theta equal to 0, phi equal to 0, the positron has to come in from theta equals to pi, phi equals to pi. Okay, but since it's a positron, right, instead of plugging into the U's, which are the particle spinners, we have to plug this into the anti-particle spinners. Okay, so in fact, I'm going to write this out. So the right-handed anti-particle spinner, right, it's going to be square root of E, right, and it's going to be sine of pi over 2, okay, and then minus cosine of pi over 2, e to the I, pi over 2. Oops, not pi over 2, because that doesn't have that 1/2 definition to it, right? Pi, okay, minus sine of pi over 2. And then the last one is cosine of pi over 2 times ei pi, right? Cosine of pi over 2 is always 0. Sine of pi over 2 is 1, right? Therefore, okay, the anti-particle right-handed spinner turns out to be this. Okay, I think I'm not going to do the same plugin just because for the sake of time, that the left-handed spinner is going to turn out to be very similar to this, but then you just have this negative 1s instead. Okay. Okay. So we can do the same process to find the muons spinners. Okay. So notice that each thing has 4 different spins, right? Okay. But what we can do is actually use a little bit of trig identities where if we have sine of pi minus theta over 2, that's actually exactly the same as cosine of theta over 2. And then if you have cosine of pi minus theta over 2, that's the same thing as sine of theta over 2. Okay. And another thing that's important is that ei pi is actually equal to -1 just from the Euler equation. Okay, because this is actually cosine of pi, right, plus I sine of pi, right, and cosine of pi is -1, and this is actually 0. Okay, so with these trig identities, what you'll find is that for the muons, okay, applying the same thing, okay, you're going to find that most of so this is not the same equation as what's up here, right? It's not equation 611, okay, where the outgoing muons is going to have this angular dependence to it, okay? This is where this angle is going to come from, okay? Where the muon, right, right-handed, is going to have this spinner, where it's cosine of, well, theta over 2, where theta is this outgoing angle, okay? Sine of the theta over 2, cosine of theta over 2, sine of theta over 2, okay? And the muon that's left-handed is going to have a very similar thing, but then you have these sines and cosines switch a little bit, okay? I think we'll probably have a little homework to play around with this, okay? And then the antiparticle right-handed and the antiparticle left-handed will have these spin, these angular dependence in their spin states. Whew. Okay, so now, right, let's put all this together and see what happens, right? Okay, so let's pick one particular helicity pairing just to see what these calculation looks like. Okay, let's pick the muon. So which one do we pick? I think this is the pairing of J. So this particular current one, right, is the muon current, and then it's the P3 bar, right, for the muon, which is the outgoing particle. So that's why that bar is there. Right, you have this gamma nu thing, right? This is the Lorentz index, okay? And then you have the antiparticle. So this is the mu minus, mu plus, okay? So what we're going to do is we're going to write these in a way so that we can actually have a little bit of a easier time to deal with these currents, okay? So in general, okay, you can write, some, let's just write, let's write the psi bar, right? That's the same thing as writing psi dagger, gamma 0, right? And this is in general, right? Whatever that spinner is, right? Daggered, okay, e to the I p dot x minus et, okay, and then gamma naught still. What you can show is that if you have nu equal to 0, okay, and then if we put a psi here, where psi, right, is another spinner, right, mu without the u without the dagger, e to the I px. In this case, actually we want the antiparticle spinner, okay, because we want this part. Okay, so that put a little minus sign here, like this. Okay. When you calculate for nu equal to 0, okay, so we're doing this one piece at a time. Okay, this turns out to be basically psi 1 star, phi 1, psi 2 star, phi 1, phi 2, psi 3 stars, phi 3, psi 4 star, phi 4. Okay, and this basically turns it into U1, 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 V1, sorry, and then U2 dagger, V2, and so on like that. Okay, so that's what these current will look like if you try to do one of those index at a time. And I'm not going to go through the rest of this, but these are what they're going to turn out to be. Okay, the e to the minus px and the e to the plus px minus et doesn't matter, because when they multiply together, they just get e to the 0 and you get 1. Okay. By plugging in like one of these possible helicity state combination, let's say we're going to deal with, this is the, let me make this a little bit bigger, right? This is actually the outgoing muon, right-handed, connecting to the anti-muon, right, with the left helicity, okay? Okay, if we plug those in here, okay, basically plugging these giant equations in here, what's going to happen is that J0, right, we're going to follow this equation here, okay, it's going to be whatever the energy is, there's two, so because each of them let me just copy this down here so that we can see it easily. Okay. So we want to U up, which is right P3. Oops. Square root of E. I'm just copying down what's up here. C S C S. Okay, I'm going to copy down V down P4. Okay, this is the muon with the right-handed helicity. This is the anti-muon with the left-handed helicity. You get a square root of E here also. Okay, so that's this one. Okay, oops. S minus C, S minus C. Okay, I'm just copying them down from up on high. Okay. All right. When you do these calculations, what's going to happen is that you're going to get, well, two factors of E's. Okay. And then basically these are going to be dotted into each other, right? So you have CS. Let me just highlight them. CS, right? And then you have S and then minus C. So you have S minus SC. Okay. And then you have CS again. Just remember these are cosine signs of theta over 2. Okay. And similarly, you get this last factor here. Okay. Funny thing is, look at this. Okay. Well, see, whatever the angle theta is, okay, we're going to find that there's going to be a trig identity that allows you to figure out that, well, this is going to be equal to 0, and then we'll probably play around with that in the homework. Okay. So that's the case of the, oh, did I label these helicity states incorrectly? Yeah. Oh. So this is actually L, right. Sorry about that. Yeah. So because these are antiparticles, they should be oppositely labeled. This is going to be left. This is going to be right. Sorry about that. Okay. Okay. And this is actually going to be right. Okay. Okay. Similarly, J1, okay, is going to be this whole thing, and then you just do this multiplication thing here. What happens is that then you end up with -2 times the energy cosine theta. Okay. And similarly, for nu equals to 2, nu equals to 3, you're going to get these factors here. Whew. Okay. Let's see. Oh, yeah. No, I didn't label them wrong. Sorry about that. I think I uncorrected myself. These are the left-handed antiparticles. Always get these signs flips. RL. Yeah. Sorry about that. Okay. So putting this all in 4-vector form, okay, these J's, okay, what it's going to turn out to be is that this J mu, so this mu is the indicating that this is the muon now instead of the index. Okay, this is the muon. Okay, and this is the, in fact, the muon that has the right-handed helicity for the particle muon to go out, and then the left-handed helicity for the anti-muon going out. Okay, all right, and that's exactly what this calculation is. And then so if you put this all together, well, the first component is going to have 0. Okay, and then if you factor out a common 2e amongst all of these, okay, you factor this 2e out, do that in red. Okay, what you'll find is that, well, the second component is going to be negative cosine of theta. The third component is just I. The fourth component is going to be sine of theta. Okay. Okay. So hopefully we're going to get a little bit of practice besides me messing up the helicity twice and then correct it myself. Okay. What you'll find is that we're going to have a homework problem on this. Okay. Well, this is just the J mu RL is just a copy of this. Okay. What you'll find is that J mu RR actually all the component turns out to be 0. J mu LL, left and left, all the components turns out to be 0 also. And then J of the muon current, the opposite direction, the left-handed for the muon and right-handed for the anti-muon. Okay, it's going to have this 2e, but then you have this negative I instead. Okay, that's the difference between by switching the R's and the L's. Okay, so it's interesting that the two of these currents are 0. Okay, and we're going to talk a little bit more about this when we talk about chirality, okay, which is a conserved quantity in quantum electrodynamics, and we're going to see this in section 6.4 in a couple of sections. Okay, right. So we can do the same thing to calculate all the electron current, okay, but what we're going to do is we're going to do a little shortcut, okay, because looking at these currents, right, so the J mu, the muon current, nu, is the one we just calculated, okay? The electron current with the index mu, right, looks very similar to this. The only difference is that this is the antiparticle, this is the particle, this is the particle, this is the antiparticle. So they're kind of flipped, right? Okay, so the trick is actually if we take the Hermitian conjugate of the muon current, meaning doing this dagger thing, okay, when you do a Hermitian conjugate, this distributes to all these parts. Well, actually, before we distribute it, right, we want to write this adjoint as just U of P3 dagger with the mu gamma 0, just to be clear which one we're daggering, which one we're not. Okay. When you do this Hermitian conjugate, what happens is that it basically flips the direction, flips the order of everything. Okay. Okay. So this turns out to be here, but then it's Hermitian conjugated. This turns out to be here, Hermitian conjugated, gamma 0's flip, moved, right? Hermitian conjugated, and use of P3 also goes to the end now, but Hermitian conjugated, but they canceled out the other one, right? Okay. Since these gamma matrices are the same or Hermitian, okay? Okay. Therefore, right, gamma 0 Hermitian conjugate is still gamma 0, okay? And then gamma 0 times these gamma 0, 1, 2, 3, right, Hermitian conjugates, these are also Hermitian, meaning this part is the same thing, okay, with the order switch, so just be careful about that. So this one you have the Lorentz 4-vector version of it first, and then 0, and then you have 0, and then the Lorentz, the gamma 1, 2, 0, 1, 2, 3 on there, okay. So we reabsorb this back into our adjoint, okay. Now, right, you have V bar gamma mu times mu of P3, and that's now in the same order as what we have for the electron. Okay, I don't know if this is make it easier or harder, but this is a nice shortcut instead of re-deriving everything that we did before, right? Okay. Similarly, the way we found that there are two of them are going to be 0, the RR and LL. For the electron, it's going to be the same, where the RR and LL version of it will also be 0. Okay, but then the current is going to be 2 times the energy of the incoming particles. Okay, 0, negative 1 I. Okay, then that's because you don't have the sine cosine situation anymore. Where is it? The one up here, right? Because, right, in the incoming particle case, right, the incoming electron, right, theta is equal to 0. The outgoing electron, theta is equal to pi, not the outgoing. The incoming anti-electron, right, the positron, theta is equal to pi. So you can actually put in the values for these. Okay, so most of these will have the either ones and zeros. Okay, so this is the current for the electron. These two, we skip the ones with zeros because they're zero now. Okay, are the outgoing current for the electron, for the muon. Okay, and that's what we're going to plug in order to calculate the matrix elements. Okay. Whew. This is a really nice process. We're almost there. Okay, this is where. Whew, this is a long lecture. Okay, so let's do a one pairing example. Let's say the electron is right-handed, the positron is left-handed, the muon is right-handed, the anti-muon is left-handed. Okay. Okay. So this can be calculated by just taking the vector dot product. Oops, forgot the dot here. Of basically J, the electron current mu, with the muon's current nu. Okay. Okay. Right. So when we do this dot product calculations, we just write out their four vectors. So this is just a copy of this. This is just a copy of that. Okay. Right. You're going to get a factor of 4 times the energy, right? Right. Yeah. You're going to get a factor of 4 times the energy. So I think Thomson is skipping some steps just so I can, he's testing my algebra-ness of this, right? So let's keep the E square, and then you have S on the bottom. Okay. Okay. If we factor out 4E, right, squared, right, this is actually, since S is equal to P1 plus P2 squared, right, and this is actually going to be, since we only have the energy component because the spatial component cancels out, so this is actually 2E squared. So S is actually equal to 4E squared. So these actually completely cancel each other out. Okay, what remains here are these dot products between these vectors. 0 times 0 is 0. Negative 1 times cosine. Negative cosine gives you a cosine. Okay. Negative I times negative I gives you a 1. 0 times sine is 0. Okay. So you end up with basically E squared times 1 plus cosine theta. Am I missing a negative sign here? Where did I lose a negative sign? Oh, okay. There's my negative sign. Okay. So this is not a copy of this, right? Because when we move the index from upstairs to downstairs, right, we're supposed to negate this, right? So this is actually positive. It's actually negative. This is negative. Okay. So therefore, both of these are actually going to be negative of each of them. Okay. Wow. Okay. So if you factor out that negative 1 sign, cancels out with this one. So you get E squared times 1 plus cosine theta. Okay. And since alpha, right, is E squared over 4 pi, we can replace this E squared with 4 pi times alpha. Okay. Just to shorthand a few more things. Okay. From the symmetry of just swapping the left and right-handed particles, okay, this only works for QED and quantum chromodynamics, where this handedness is actually conserved. It doesn't work with a weak interaction. We'll see that later. Okay. We can see that while swapping these indices, these spin labels, okay, will give you the same results. Okay. So therefore, right, both of these are the same as each other. Okay. And what we can do is we can do the same thing, and I think maybe that'll be another homework problem. We're going to see that if we are swapping, so to see the difference here, we have right to right, left to left, right? Let's not think about it that way. It's actually right left to right left, or left right to left right. Okay, this one is right left to left right, so the helicity of the particle and antiparticle actually swap with each other. Similarly, right, this is left right to right left. Okay, so once again, the helicity of the particle and antiparticle also swap with each other in this case again. Okay, doing the little homework again. Okay, we're going to find that the only difference between them is going to be a negative sign. Okay. Okay. And since this is the matrix element squared, okay, we're going to find that, well, you take this square, okay, you have this 4 pi alpha square, and then you have 1 plus cosine theta square, okay, for the one that does not swap helicity between the particle and antiparticles. Okay, the ones that does, you're going to pick up a little negative sign here. Okay. Okay, almost there. So we're going to average over all the incoming helicity and out helicity states, right? Where that 1/4 comes from. Okay, so this first term here comes from up here, so that's going to be, right, this is the matrix elements to calculate if you have a right-handed electron and a left-handed positron annihilating and producing a right-handed muon and a left-handed anti-muon. Okay, and similarly with these other 4 terms. Okay, these are 4 possible incoming helicity probabilities. Okay, sorry, incoming and outgoing. Okay, because a lot of the, remember that it used to be 16 of these, right? Because we have 4 possible incoming, outgoing, but we found that 2 out of the 4 is 0, so therefore we just have 2 by 2, which will give you 4 of these. Okay, all right. So, okay, plugging these numbers over here, right? Okay, doing a little algebra. I'll let you do that. Okay, you're going to get that, well, it's going to get e to the 4th power. Okay, I don't know why he keeps switching between alphas and e's, but that's okay. Okay, but then these squares, this is going to give you two factors of 1 plus cosine theta. This is going to give you, nope, yeah, he's just being really nice to me, isn't he? These two are going to be the same. These two is going to be the one that's minus. Okay, give you 2 factors of each. Okay, these 2 factors, if you do a little trig identities between, well, if you multiply this out and then do the addition and subtraction, what you're going to see is that you're going to get another factor 2 here to cancel out this factor of 1/4. Okay, and then the end result is going to be e to the 4th power 1 plus cosine square theta. So be careful, this is the very different function, right? Okay, now we have that, we can plug that back into our cross section, or actually technically the differential cross section, right, equation, because we can't do the integration over the angles yet without knowing the angular dependence here. Plug that back in here. So the differential cross section you're going to get is going to be e to the 4th power times 1 plus cosine square theta, and then this piece is just what was there before. Okay. Once again, we're going to replace these e squares with alphas. Okay, he keeps swapping back and forth between the two, but that's okay. What we're going to see is that if you do that substitution, you're going to find that the differential cross section is going to be alpha squared divided by 4s times 1 plus cosine square theta. Okay, now we got to this result. I'm not sure how long this recording has been going on, but we'll see afterward. Let's think about what this means. Okay, let's interpret this a little bit. Okay, this differential cross section is proportional to alpha squared. Okay, checked, right? Hopefully that's the case, right? Because we know that the lowest order cross sections, right, is going to be proportional to the matrix element is proportional to alpha, but since we're squaring the matrix element, it's going to, so this cross section is going to be proportional to alpha squared. Okay, is inversely proportional to the center of mass energy, this S here, right? Squared. Forgot the square. Okay. So basically, the higher the energy, the smaller this cross section. And maybe you have some intuition about this, right? Right. When you have two particles flying into each other, right? The faster they go, or more center mass energy, the less time they're going to spend near each other. So therefore, right, there's a lesser chance for them to annihilate and run into each other. Okay. So let's talk about a special case, right? Let's say if theta is equal to 0 or pi, meaning you have two incoming particle coming in. Instead of my hands, let's just draw it, right? Okay, you have, let me set up the x-axis, the z-axis, right? This is the z-axis, right? So you have the positron coming in, the electron coming in like this, right? Okay, so let's say, right, the muon comes out at theta equals 0. So let's say this is the mu minus, and then theta equals to pi, mu plus, right? Okay, right? If you plug this into here, right, you're going to get that, well, cosine of theta, well, cosine square of 0 is going to be 1, and then that actually gives you a factor of 2 here, right? So the cross section is actually the most likely, right, where there's no, where the annihilation happens, and then the muons come out in the same direction as the E plus E minus. Interesting. Okay. I can switch this around, right? Because, right, theta could also be pi, right? Let me add this. Let's do this. Let's do the second process instead, okay, instead of overwriting it, right? Right, same thing here, E plus E minus, right? And now, right, theta equals to pi, so that's mu minus, and then mu plus, okay? It's equally probable for the muon to come out in the opposite direction as the electron, and the mu plus to come out in the opposite direction of the anti-electron, okay? And this is actually a pretty cool symmetry for quantum electrodynamics. It actually does not care whether or not something is a particle or antiparticles, okay? Okay. In fact, the symmetry of 1 plus cosine square theta means that, you know, the particle, let's use this one, the particle is equally likely to come out this way as the backward direction. So this is actually an interesting symmetry of the quantum electrodynamics where we only have a photon involved. Okay. In fact, we can experimentally confirm this with data. So I'm an experimentalist, so therefore data is the thing I actually want to look for. Okay. So the plots below are from this experiment called JADE, where they collided E plus E minus together, and then sometimes it'll produce mu plus mu minus, and they capture these, and they even measure the helicity of these particles, and therefore they can actually differentiate the different parts of the differential cross section that we just calculated. Okay, so let's go through and read this plot. So let's start with the left-hand plot here. Okay, so this is the differential cross section of cosine theta. Okay, so this is plotted versus cosine theta. Okay, so what that dotted line stuff is the actual data itself that they found. Okay, so this is the combinations of a left-handed electron with a right-handed anti-electron, and then a right-handed electron with a left-handed positron colliding, producing a right-handed muon and a left-handed anti-muon. And I'm not going to repeat this again, so you can see the same thing here. Okay, and that's what this distribution looks like. Okay, right? Okay. Remember, this was from the 1 plus cosine. Wait, this is where they swap, right? Yeah, this is the contribution, where it's 1 minus cosine theta squared, like this. Okay, and the one that the helicity don't swap is actually 1 plus cosine theta squared, right? When you add them up and you average over all the possible incoming and outgoing spin state, then you get 1 plus cosine square using, just some multiplications of cosine. And this is the combination of both of them together. And we see that it actually behaves exactly like a 1 plus cosine square theta function. Okay. In fact, this is actually the data point that's plotted on the right. So the dots with the error bars, that's the actual data from the experiment. Okay. This black line, right, is 1 plus cosine square theta. Okay. Right. And this dash line, let me see what that's dash line. Oh, the dash line is a little bit of electron weak correction. Okay. So by electron weak correction, that means, maybe not all of them interacted with a photon. It could have done this with a Z also, which does not obey the same symmetry as quantum electrodynamics. Okay. That's why this dash line here is slightly different from 1 plus cosine square theta. Okay. All right. Just to wrap things up, almost done. Sorry. So the total cross section can now be computed by just doing an integral. Okay. If you want to integrate 1 plus cosine square theta, right? You can do a U substitution where instead of theta, you change this to cosine theta. And we do this integral from -1 to 1, meaning theta equal to 0 to theta equals to pi. What happened is that you'll see that this integral actually comes out to be 16 pi divided by 3. Plugging in that number into the differential, converting this differential cross section to the cross section, you'll find that it's just going to be 4 pi alpha squared divided by 3 times the center of mass energy squared. Okay. All right. Let's try to wrap this up. I've been talking for too long already. Okay, so the calculation above is actually valid only for the center of mass frame. Okay, but what we can do is actually write the Lorentz invariant form by keeping the 4 momentum that we wrote. So instead of writing things in terms of thetas and along some direction, right? Settings, thetas and phis to some angle, what we can do is that we just keep these 4 momentums. Okay, since P1.P2 is going to be twice the energy squared. Okay, and then P1.P3, these are 4 momentum dot products, is going to give you E squared times 1 minus cosine theta, and similarly P1.P4. So maybe we'll play around with this in the homework to practice some 4 momentum dot products. Okay, going to be E squared times 1 plus cosine of theta. So this will be in the center of mass frame. But since any dot products of 4 vectors are Lorentz invariant, these values are also Lorentz invariant. Okay, so therefore you can replace anywhere you see in the matrix element, 1 minus cosine, 1 plus cosine, right, and then 2 e's with these 4 momentum dot products. Okay, and therefore the average, the spin average, the helicity average matrix element squared, okay, is going to be 2 times the energy times these 4 vector dot products. I'm not even going to read them out, okay, but you can see that on the screen. Okay, the dot products of these variables can be expressed in these Mandelstam variables, of course, okay, where S is going to be equal to m1 squared, m2 squared, plus twice the dot product between P1 and P2. But in the case of this relativistic case, right, we can just ignore the masses, right? So therefore, S is actually equals to 2 times P1 dot P2. So we can actually, if we divide this by 2, right, we can replace this with that, okay? Similarly, right, the T channel Manos length variable is going to be minus 2p1.p3, and then U is going to be minus 2p1.p4. So you can do all these substitution up here, okay? And then you can write the matrix elements in the form of this Lorentz invariant form, where it's just going to be 2 times the electric elementary charge square, and you should probably convert this to alpha anyway, but multiplied by t squared plus u squared divided by s squared. Okay, and then you can actually do this calculation without picking any reference frame, but unless you pick a reference frame, until you figure out what theta is, because theta is not Lorentz invariant, okay, you cannot do any further calculations. All right, and in fact, actually, before I end the video, right, cross sections, right, depends